Okay, yeah, thanks for having me here. So I'm Jiajun from Stanford. I'm going to talk about our work on understanding visual intelligence through physical intrinsics. So if you were, maybe a few of you, probably very few, but a few of you maybe at the event yesterday. So this is going to be an expanded version of what we talked about yesterday. Okay, where's my mouse? Here. Okay, great. Um, let's see. No, we live in this virtual world, and then the world has a lot of intrinsic, in some sense, intrinsic structures that are there in the world. Actually, sorry, I have to. Oh yeah, I guess it's okay. Yeah. Um, to understand the visual world, right? So to understand like the world we live in, that the scenes have objects and objects have physical properties and geometries. So sometimes we wonder, is it possible for us to leverage these kind of underlying physical structure for us to build systems that can be much more efficient and much more generalizable in seeing, understanding, and generating the world. So that's basically the theme of the talk. Okay, so we see all these 2D pictures. And um, when we see a picture of a lion, all right, we understand, it's not just the pixels. There's an underlying physical process that the objects have underlying, okay, great, geometries and textures and materials, and they interact, and then they produce the pictures we see here. Right. So the process of, and we have spent all the time, like maybe multiple decades and not even centuries, to study how these physical properties are supposed to interact and produce the pictures. Right. So that's what we call physical simulation. And in computer graphics, we study not only physical simulation, we also study rendering. Right. So you take all these like geometries and lighting, you think about okay, how the things are going to evolve, and under the lighting condition, how the pictures will look like. So you render and produce these pixels. So for a long time, maybe people talk about it a bit less now, but I think it's very relevant to all the Bayesian talks we heard in the morning from Joanne and from Jun, right? So it's like, oh, for a long time, people thought maybe we want to invert the process. So we think vision as inverse graphics, and you want to de-render the visual input and produce these underlying causal factors, such as the geometries and textures and motions of objects. Ideally, you want to have a distribution of it, right? So that's you have a Bayesian view of, how vision is inverse graphics and sampling these properties. Okay, so we still want to solve these problems, but now we're in a different era. We're in a data-driven era, and everyone wants to learn from data. And ideally, if you have annotations, learn from supervised data is always the best. But unlike the case where you have a picture, you can say, this is a lion, or this is a cat or a dog. And nowadays, you can probably use vision language models to get annotations on the semantics of objects. It is actually very hard to get annotations on the materials or physical properties of objects, right? So for 3D, you may have some annotations. For physical properties like materials, you almost have zero annotations. So if I don't have any annotations, how can I get the physical properties I care about? So I'm going to present maybe I'll say two different ideas on how we have been exploring to get these object properties that you care about without requiring too much annotations. So the first idea is we want to use these intrinsics or physical properties as inductive biases for self-supervised learning. Okay, I'll try to use this. Okay, so I have all the image and visual observations, and I want to get things like object, geometries, and materials out of it. I don't have annotations here. What I do know is how these properties are supposed to interact with each other. Right? As I said, this is the subject of physical simulation and computer graphics. So I can take all these, in some sense, physical knowledge, but have them as part of the learning systems. Right, so the simulation pipeline can be integrated in the loop of the learning systems. And of course, if I want to build the deep learning systems, the simulation pipeline has to be differentiable. So I can have a differentiable simulation rendering pipeline. And therefore, without having, uh, this one doesn't have a light, right? So can I actually, okay, I guess it's okay. Um, without having annotations on all the intermediate representations I care about, but because I do know how these properties are supposed to interact with each other and reproduce the observations I have. So what I can do is I can now think about it as an autoencoder, but instead of having autoencoder in the representation, intermediate representations to be latent, now I have some sort of interpretable representations, and as well as how these interpretable representations are supposed to be combined to reconstruct the output in a differentiable way. Then what you can do is you can do self-supervised learning, right? So this is, I guess, it's not, yeah, okay. So now what you can do is you can do self-supervised learning. I don't have annotations in the middle, but I use my annotations on the raw input just by seeing how my pipeline is reconstructing this visual or multimodal input, and I automatically get all these physical properties for free, right, in some sense. And during training, I can train it on these unannotated images and videos. And during testing, may even just be able to take the first half so that I can go from a single image and reconstruct and get the physical properties you care about. So I'm going to give a few examples about what we did in this line of work and following this paradigm. One example is in the case we have a bouquet of flowers. In this case, I have 50 roses roughly in this bouquet. And I understand, right, these are different roses. And so maybe I want to ask a question that is, okay, what makes these rows look kind of all similar? They're not identical, but they look kind of similar. So what really makes a rose look like a rose compared with, maybe I have a remote, which is a bit hard to use actually. So what is the difference between a rose and a remote, right? So we realize these different roses are just multiple instances from the same object category. And the fact that they belong to the same object category and the remote belongs to a different object category is because, at least this is our observation, is they share the same underlying distribution of object intrinsics, right? So there's an underlying distribution of object geometries and textures that form the category of a rose, which we would like to learn and model. And what is going on here is you can think about it as the nature is running the generative process, sampling from this distribution so that I can get a rose of a particular geometry and texture. I can put it couple it with extrinsic factors such as its pose and lighting conditions. And then I can see all these different roses that look kind of different but similar. So by taking this observation as a very weak inductive bias, what we can do is we can learn a Jiajun model, right, sampling from, let's say, a Gaussian distribution to get object geometries and textures, albedos. And I can put it together through a differential rendering pipeline about how the lightings and poses of rows are going to impact its appearance. And you can get a rendered rows. Of course, your goal is to make this rendered rows to be as close as the real rows is. And so we did this work 3 years ago, and back then we just used a discriminator, like a GAN style. But of course, nowadays you can use the pre-trained diffusion priors and stuff like that, score decision sampling. Okay, so very simple idea, and very, I would say, it's like very minimal supervision, but you can actually get a lot of it. So what you can get out of it is now, I'll play the video. You can see at the bottom row, I will be able to learn, after learning this distribution, to seeing and rendering roses from different viewpoints. In the second to bottom row, I can render roses in different lighting conditions. And in the middle row, because I'm learning the underlying distribution of object geometries, I can sampling roses of different shapes, right, as well. So you may feel like the results here are not perfect for many reasons, which is very true. But the first is we did it 3 years ago. So back then, we didn't even use any diffusion priors. But more importantly, I want to emphasize that is everything we're doing here is only learning from a single image. So that all the models are training from scratch. It's not like taking an ImageNet or Dino features, anything that's pre-trained, right? Just take all the models that train from scratch and learn from one picture. And as you can see, just have one picture with the right inductive bias and physical knowledge and put it differentially into a learning system to make it easy, make the learning process easier to happen. You can actually get a lot. You can do all these different things just by learning from a single image. Okay, so this was done by my PhD student, Jiajun. And later we extended and think about, okay, is that possible for us to model multiple object categories instead of a single object categories because the object categories are not independent, right? So if I have animals like deer and horses, they sort of share the same skeletal structure. So we wonder, is it possible for us to not only discover object geometries and textures, but also their shared skeletal structure? So this is what we can do here. What we did is we train internet images and videos of unannotated animals. We have 100 of them, but they're all quadrupeds. So we do make assumptions here. There's no fish, there's no snake, but we can learn from internet images and to reconstruct these 100 different object categories of their geometries and textures. and their skeletal structure, so that you can sort of animate them in roughly the same way. They can all behave in a certain pattern. You can of course sample their geometries as well. So this is what we call the work on learning the 3D fauna of the web. It was led by Jiajun, who is my PhD student, and Elliot Wu, who was my postdoc back then. Now he's an assistant professor at Cambridge. And and Elliot actually did his undergrad in Hong Kong at HKU. Okay, so we also extended this work a bit further. So think about how can we not only just doing reconstructions, but also maybe once you discover the analytical structure and skeletal structure, and you should be able to also rig, right, and animate these objects. So what is going on in the standard rigging setup is you have an object, and you want to discover the skeletal structures, but you also want to discover the skinny weight, so that you can think about how these control points are going to impact the different surfaces on the object geometry, and therefore you can edit it, you can produce objects in different poses. So it also fit into our pipeline pretty well in the sense that we can now do, it's not fully category agnostic, but it's pretty much category agnostic rigging by discovering, as I said, object geometries. In this work, we didn't think about texture, so just the geometry, the skeletal structures, but also how the skeletal structures and the controlling points are going to impact their geometries. Again, in a mostly self-supervised way, right, by reconstructing the objects in different poses. And we can actually have shared architecture, right, as a category agnostic. And you can go from unannotated, in this case it's maybe unannotated object shapes, to discover the skeletal structures and editable blobs. And you can move the blocks, and you can see the objects now moving to different configurations. And it is, as I said, it's doing self-supervised or unsupervised training, right? So we disentangle the intrinsic parameters, such as object opacity or embedded features, which is like the latent representations for the geometry, with the extrinsic factors, right? Similar to Roll's cases, we have the positions and rotations, which are extrinsic to the objects. And when you're doing editing, right, so the intrinsic parameters should not change. What is really changing is the extrinsic parameters. So you can keep the intrinsic identity embeddings, change the pose factors, and you can regenerate the output shapes and then use it in a self-supervised way to learn the features that correspond to the intrinsic identities of these animatable objects. Here are some more results, which you can reconstruct the input, and you can move parts of the animals. You can scale part of animals to make it fatter. You can remove a blob so that the leg becomes shorter, or you can even produce some of these out of distribution generalizations as well. And so this is also led by Elliot, but now also with my PhD student Chen and Guangzhou, who was an undergrad back then, but now he's a PhD student at Cornell. Related to that, we're also trying to build somehow there's always a problem that I want to run Windows on Mac. But anyway, you can go to our papers and see the raw table. But we built a data set. It's just one slide, very simple. We built a data set by filtering observers, which is not too surprising. But it's also, I'm not sure if it's even better than some of the work that people here did. So anyway, but it's similar to even some of the people our colleagues at Hong Kong University did. In filtering by filtering observers, we can get animate data sets, which we have these animatable, articulated objects and the ways that you can interact with them. But I do want to highlight this is also led by Elliot, who did his undergrad in Hong Kong and recruited 2 other undergrads from Hong Kong, Yufan and Yuhao. They're actually all from the same group from HKUST. And Yufan is now a PhD student. They're both PhD students. I think Yuhao is at ICL, and Yufan is maybe at Austin, or I can't remember, but all these kind of good places. And very lucky to have all the very strong students from Hong Kong as well. Okay. So this is sort of summarizes our idea behind the first paradigm, right? So how can we leverage these I would say intrinsic physical object properties and the ways that they interact with each other to really get a lot for free in some sense from unannotated images and videos and shapes. But the system has some kind of features, but also is a problem. It does have a simulator in the loop. As I said, it gives you all the supervisions for free, but it does come with some limitations, right? By having these kind of intrinsic structures or the physical simulators in the loop, then it comes with constraints include, for example, the simulators has to be differentiable. And there are some things that we know how to simulate differentially pretty well. There are a lot of things that we don't really know how to simulate differentially, or we don't even know how to simulate at all, right? So there are issues with requirements come with differential simulation that is kind of constraining. And there are issues with, you have to have precise supervision or precise simulation. But when the scenes involve objects of different matters, like fluids or deformed objects and soft bodies and rigid bodies, and they're interacting with each other, then very accurate simulation is also very hard. Sometimes you can simulate something pretty accurately and differentially, but it's very slow, right? In computer graphics, you can have differentiable ray tracing, which is very accurate and is differentiable, but the forward pass takes seconds, if not longer. But in the case of, we want to integrate it into learning systems, then going through backpropagation, right? Feed forward, backward. You want the simulation step to be probably be less than 100 milliseconds. So it also has to be fast. So it's in some sense, it's really hard to achieve, all these constraints. And of course, there are, I would say, a lot of researchers, but also even startups that are very well funded on trying to resolve these problems by building much better, much more generalizable, and much faster differentiable simulators. So maybe this will be addressed in 5 years or 10 years. But right now, because it hasn't been addressed yet, it does come with all the constraints. For example, in many of these work that I've shown, I think the ideas works very well if your domain does fit these assumptions. But the assumptions often include there's only a single object in the scene or a central object in the scene, there's a clean background, there's uniform lighting conditions, or you have to assume some level of rigidity of these objects. Okay, so that's the issues with idea one. And this is also the time that we have seen a lot of advances, partially because of signing. We're signing here, right? So I know come with diffusion transformers and all these things. We've seen all the advances in these kind of pre-trained foundation models, including image diffusion models, video diffusion models, and vision language models. And if it is possible to type in some language and ask these image diffusion models or video diffusion models to generate something that's so photorealistic to us, then we thought, even if they have all these physical consistency issues and stuff like that, they must have learned some knowledge about physics in some way. So is that possible for us to try to at least extract to the extent that they have got it, right? These physical knowledge from these pre-trained models. So that goes to the second paradigm that we have been looking into even more in the past 2 years is instead of having intrinsics as the intermediate representations for self-supervised learning systems, we want to use intrinsics as the distillation or grounding target of these foundation models. So sometimes I say you have a foundation model. It was like think about it as a visual simulator. It was maybe it's a weird term, but think about it as a visual simulator. But you want to ground it so you can turn this visual simulator into a physical simulator. So one work we did in this direction is again led by Chen, who is my PhD student. Is we look into extension of the earlier problem about modeling roses. But what is the thing that really belongs to roles, right? I was actually inspired when I was going to art museum, I think in Orange County in Irvine, and they're having this. The title of the work is actually the title of the exhibition. It's like okay, so it models roses in different ways, and I was like, oh yeah, what really belongs to roles itself. It's not just its geometries and textures. It is also its lifespan, right? So the way it grows, the way it wilts. So is that possible for us to model roses in 4D instead of 3D so that I can still see it from different viewpoints and the different lighting conditions, but you can also see it grows and wilts and do all these different things. So the problem formulation is a simple extension of our earlier problem. Approach we took is very different. So we're no longer just having them as a differential simulator in loop. We still use a little bit of differential simulation. I was actually sort of extension of nerve-like situation, but we use a lot more of distillation from pre-trained image diffusion models and video diffusion models and vision language models. We use all of them. But due to time constraint, although I have a bit more time here, I want to talk about some other work in more detail. So I'll say I'll skip this. I'll just show some results, and we can talk about this offline. But before that, let me show one more example. That is, of course, you're not going to only model lifespan of roles. You can do it for other growing objects, such as a bread being baked. You can see the bread in different lighting conditions from different viewpoints, and also see the baking process. Okay. Um, we have been thinking about how much we can do distillation from, I would say, maybe as an intermediate supervision, but now more as a distillation process or target from preaching models about object intrinsics. This includes object geometries and textures. In some sense, a little bit, but now it's an autonomous growing process. But we haven't really think about, how we can go from these autonomous motions, like animals and grow roses, how they move themselves, to really action predictions, right? So how they're going to respond to external actions. So in this case, the problem I want to address is, can we do action condition dynamics predictions of 3D objects, right? So the problem formulation now is you still have a rose, and it can be, no, actually, it was input is you can assume you have a 3D Gaussians, which you can probably even now get from a single image, right? You can do LGM and all these things, right? So you can get a single image from a single image of 3D Gaussian representation. What you want to do is you want to simulate how this 3D Gaussians or scenes are supposed to respond to your external actions like these, right? Because as action condition predictions, you should be able to also predict how the rose is going to be responding to different ways of perturbations. So compared with the previous problems, this new problem introduces this additional challenge. That is, you now have to perceive and model physical object properties, right? So geometries and textures, they're all physics. But maybe when we say physics in a more narrow definition, we often refer to these actual physical properties like densities or Young's modulus and stuff like that, right? So, but in this case, for action condition dynamics predictions, it really require physical grounding on these physical properties like stiffness. And it turns out, right, randomly assigning physical properties doesn't give you good results. That was a bit surprising to me at the very beginning because I thought just one number, right? What if you just randomly sample some numbers and maybe it would just be fine? And it turned out it was not as fine. If you just sample something, it'll be like this. And if you sample it a couple times, it's still not going to look as good. So I think for two reasons, right? So the first one is and just like why vision is hard, and if you remember what Joel talked about, all the Bayesian stuff in the morning, right? So there's this underlying narrow distribution which lies in this low dimensional manifold, which we're going to hear more actually from Ching maybe tomorrow, right? So there's I would say the real world, the physical world, actually lies in a very low dimensional manifold, and our observation is actually extremely high dimensional, right? So vision is hard because you want to discover that low dimensional space from the high dimensional observations. And for physical properties, it's the same. Although you may feel like physical properties, you already have distilled what these physical properties are, so the dimension itself is already much lower. But even the distribution of these physical properties is still hard to model. But second, the object here, they're not homogeneous. It's not a rigid body. So all you have is just a density that you wanted to be discovered. The object is heterogeneous in the sense that you can see, maybe I'll play once more, the top part of the flower and like the petals and the stems, right? They have very different physical properties. So what you need is just not a single number. It's actually a field. It's still a high dimensional representation of the physical properties at different spaces. All right. So compared with images and videos, which we know 3D data is already much less available. But physical property data is even, there's no way you almost have no data about what's the physical property or like the stiffness of these flowers. So how can we get a good estimation out of it? We again goes to these kind of pre-trained image and video foundation models because they're supposed to have learned something about objects supposed to behave. Therefore, they must have some ideas about the geometries and maybe the physical properties of our objects as well. So in this work called FitStreamer, which we're trying to do is really to convert, in some sense, a visual simulator to a physics simulator. So it was led by my PhD student, Koven, and MIT PhD student from Bill Freeman's group called Tim Yuan. So what's going on here is we already have a 3D representations like 3D Gaussians, and you can render it into a single image. You can send it to an image to video diffusion model. And what you're going to get is you can get a reference video of the flower, which is supposed to look pretty realistic, right? Because the video model must have learned how the flower is supposed to look like. But it's just a video. It doesn't give you anything about 3D or physical properties. So at the same time, you can have an estimation of the physics field or the material field. In this case, it's a field of Young's modulus. And you can couple that physics field and the geometry appearance field. You can send it into a differential simulation pipeline. In this case, we use differential material point methods, which I think was much more, it was something that has been in graphics for decades, but 1 decade maybe, before for due to it's pretty easy to make differentiable, and it has this it's particle-based representation. It has pretty natural connections to Gaussians. I think now it becomes a bit more popular. But anyway, you can just take the Gaussian representations in the materials field, send it to this differentiable simulation pipeline and a differentiable rendering pipeline. And what you're going to get is a rendered video that is, okay, how the system believes the scene, the flower is supposed to look like, given your current estimation of the geometries and the physical properties. As I said, if you randomly initialize the physical property field, it's not going to look as realistic. So you can get some video that doesn't look as realistic. But it is physics-based. And also at the same time, now you have a reference video from an image to video generation model. So what you can do is you can just compare the two. And it turned out that the system is easy to use to the extent that even if you just compute altitude loss in the pixel space directly, and once you get the loss, because the differential simulation rendering pipeline is differentiable, you can use gradient-based optimization to directly update your estimation of the physical property field. And even if you just do that, very simple, very intuitive, the system is able to learn and revise your estimation of physical property field by making the rendered output approximate the output generated by the image to video diffusion model, and eventually give you a pretty good estimation of physical properties. So here are some more results. So you can see the flowers, but because NPM, they're actually, I would say, they're best with soft bodies. So we have a lot more results on different types of soft bodies with the cables and hats and flowers and plants. I'm sorry. Oh yeah, that's right. Yeah. Yeah, that's a separate question, which we can talk more offline. Yeah, that's another, so yeah, in talks like this, you have to, yeah, but I can go into more detail on that, but that's an important question as well. Yeah. And actually, Joanne and I would spend time talking about it yesterday about how you can represent motions and how you can convert from language to motions and stuff like that. So also a complicated situation. Okay, but you can also have some comparisons with ground truth. So here you have a real capture video where you actually have a fan from the left. So we can actually capture how the flowers are supposed to respond to external actions. You can see that our reconstruction is much more realistic and closer to ground truth compared with the baselines. We also did a user study on the realism in the sense that, okay, I asked users which one is more realistic. You can see that our system is, on average, actually even preferred over real capture, the ground truth, at roughly 50%, right? Because if it's as accurate as real videos, then the user should not be able to tell, so the accuracy should be 50%, right? This is a two-way false choice. So you can see the videos are actually, generated videos are close enough to ground truth and much better than the baselines, or much more preferred compared with the baselines. Okay, so this is about soft bodies. And Coven later moved on, and he thought, can we also deal with other type of objects? And one particularly important type of object is fluid, right? So, because they have a lot of the applications in firefighting, but also in biology and chemistry and aerodynamics as well. And despite they have all these engineering applications, right now to image or measure the fluids is very difficult, right? So you may either require very expensive equipment, or they have to be in very constrained setups. And most likely you need both of them, right? It has to be very expensive setups and in constrained setups. So it's not possible for us to just use like a camera, right? So if you have a camera of iPhone, it's very easy for you to take a video and then you can reconstruct the things and see it from different viewpoints and do everything like that. Okay, so this is the motivation behind the next work I'm going to talk about called fluid nexus. And our goal here is to go from a single video so they can reconstruct this 3D fluid field and also the velocity field, the physics field. So you can see it from different viewpoints. And you can also do action condition predictions as well, right? So how the fluid field is going to respond to your actions. So compared with some existing work, including our earlier work in this direction, I think the biggest challenge has been previous works often require multi-view as input, right? And now we want to just take a single view in video as input. And you want to make predictions. You just not only want to reconstruct the visual scenes, but to also predict what's going to happen in the future. So if you look a bit closer into it, I think there are three different challenges. The first is, okay, if you only have a single view, right, how can you really get reasonable 3D information out of it? So the approach we want to take is we actually do a single view to normal view generation. But single view to non-view generation is not really solved. And if you use the existing method, it doesn't work as well. So you need some changes there. And the second is once you have some kind of a maybe multi-view information, how you can reconstruct the 3D fluid fields, but not only just its appearance, but also the physics, right, the velocities. And finally, even if you do have the appearance and the velocity, how can you go from just reconstruction to prediction, right? So there's some kind of challenges in each of these directions. Okay, so in this work, which is led by, again, Koven and Yue, who is my new PhD student, we think about how we can couple physical representations with, again, video generation methods. So we make innovations in each of 3 stages, thinking about how image and video gen can help us to go from a single view input video to multi-view videos, and to fuse multi-view videos through a 2-layer particle, actually visual physical representation, so they can do 3D fluid and velocity appearance and velocity field reconstructions. And finally, how you can, based on the reconstructed fluid fields, to do generative predictions in the sense that you use physics-based predictions, but also augment it with generative models to make sure the output is more realistic. So let me go a bit more into detail in each of these directions. So in the first stage, I have an input video. And what we can do is we just take existing methods like 0, 1, 2, 3, right, which is takes the input view, and then we can generate novel views, but we generate it per view and per time step. So that leads to 2-level inconsistencies, right? The first is there's a multi-view inconsistency because the things you generate from different views are not supposed to be consistent with each other. That's actually a big problem with 0, 1, 2, 3. And second, there's temporal consistency because you're generating every image per frame, per time step. So the things are going to fluctuate a bit. We can resolve that by, actually there's an issue here, but I'll say this can be resolved by taking a video diffusion model, which is trained on multi-view input, so that you can do a denoising process and take these kind of noisy, in some sense, you can think about it as noisy multi-view videos, but trying to fix them, right, through our image and video editing pipeline, SDEdit, so that you can get a refined video, which is supposed to be much more multi-view consistent and temporally consistent. But just to be honest, right, I think there's a caveat here is, okay, to fine tune, there's no existing models like that, so you have to sort of fine tune it a bit. And to fine tune it, you have to take multi-view videos as input or go on to annotate it, not annotate, to collect it, but they have to be multi-view consistent. So where do you get these multi-view videos is a big problem. So in our case, we actually have to collect some data ourselves. So that leads to some kind of a challenge. You don't need a lot because you need fine tuning, so you don't need that many, but collecting these multi-view videos are still a pain. So hopefully we can address that in the future. But now, once you do have this editing pipeline, you can have much more consistent, multi-view videos, which are pretty close to the ground truth, right? Compared with earlier work that we did on single null-view synthesis for these fluids, now it works much better. In the second stage, we want to think about once you have the reconstructed, more or less consistent multi-view videos, how you can reconstruct the 3D fluid fields. So we have a representation that have 2 layers of particles. One is for physics, the velocity field. One is for appearance, the radiance fields. So you can see we have 2 layers of particles. We have velocity particles, and we have appearance particles. Okay, so this allows you to have 2 types of losses. The first is appearance loss, because you can render from different viewpoints and stuff like that, and you get multi-view data, which is, in some sense, you generate it, derive yourself, but that can allow you to correct your estimation of the appearance particles. And you can also take whatever physical constraints that you may already have and apply here, such as Navier-Stokes equations or the momentum and mass conservation losses. So in every time step, what you can do is you can have these velocity particles and the radiance particles. You can run a physics simulation so that the velocity particles are going to move, right, based on physics. You can integrate their motion to also compute how the radiance particles are supposed to move. And after that, you can refine these estimation of the radiance particles using appearance loss, because now you have how they should look like from different viewpoints after rendering, after differential rendering. And you can revise your estimation of the physical particles by using the physics loss. So you can get some supervision to move these particles. And then you can iterate this process, right, for every time step. So you can do that iteratively, and eventually you get estimation of these 40 particles, right, the 3D particles at every time step. Okay. So you can see that without the physics loss, the thing's going to dissipate. You have these kind of I would say, drifting errors, right? It's very common in video predictions. It just doesn't look as good over time. But with the physics loss, things look much more realistic and closer to the ground truth. Still kind of blurry though, so that's kind of a problem. But at least it's just quite some improvement. Okay, and finally, once we have the reconstructed fluid fields, now how can we do predictions? One idea is you directly take the estimated appearance particles and velocity particles and just run physical simulation. But you have the same problem. That is, if you do many steps of forward predictions, it just looks kind of very blurry. So we thought, is that possible for us to also use the video generation models or preaching foundation models to help us? So what is going on is I can run physical simulation, and as you can see over time, it doesn't look as good, and you have more artifacts. But we can sort of correct it. And we can say, okay, because these video diffusion models have sort of already seen what these realistic videos are supposed to look like. So if I take the predicted videos, which is not as accurate, but trying to denoise them, right, and then let it go through a video diffusion model, then I'm going to get much more realistic, visually realistic videos. And but it's a video, right? So and finally, I can use my, if you remember, the differential appearance loss and physics loss, so that I can use them to re-optimize the underlying 4D particles based on the guidance provided now by the video diffusion models, right? So finally, I can get a 4D reconstruction and predictive future using these 4D particles, but you can also see it from different viewpoints. Okay, so yeah, again, this is done by Coleman and Yue. We call this fluid nexus because it really connects, two types of representations. One is generative or visual, one is physical. And you can have non-visual synthesis results from different viewpoints. And you can think about how the scene is supposed to look like if you have fluid interacting with the rigid body. And you can do future predictions as well. Yeah, and one more example of future prediction. Okay. So the real world has more than just fluids and soft bodies. So we thought, is that possible? Actually, we really is Coleman. He thought about how can we really go beyond just modeling specific types of objects to model all these different types of objects that can be integrated and interacting with each other. So what he did is he wanted to build upon his totally different and separate line of work, which I only have time to use one slide to cover, is on 3D scene generation. So what he did in this earlier work is called Wonder World. It was for real-time or close to real-time interactive 3D scene generation. So what you can do is you can upload a single image and you can control the generation process by, system going to first turn the image into 3D, and then you can move to different directions, and then you can say, oh, I want to move to the left, and I want left scenes to look like an Asian courtyard. Right, so you want to make sure I have all these 3D scenes that are realistic and connected and smooth, but they're all in 3D so that I can move around. And I can go to the right and I want to have a coffee house or a cyberpunk city, stuff like that. Okay, so you do all these in close to real time, but everything here is just static. So he thought, is that possible for us to bring back all the differential, deformable object simulation, fluid simulation into this scene generation framework? So the problem we want to solve now is you have a single image. You want to turn the image into 3D, and then you want to apply 3D actions so that you have an interactive 3D scenes. In this case, the rubber duck, which is more or less rigid, is able to interact with the fluid field. Okay. So here I have a teaser video, which I think nicely summarizes the main results of the work. So I'm going to first play the video. And yeah, I should really emphasize that the output they look like a video, but there's always an underlying 4D representation so that you can move the camera, you can see how the scene will look like from different viewpoints as well. Okay. So the idea behind it is, again, very similar. and now I can even finish it much faster because I just talked about fluid nexus. Is simulators are great, but they have some issues, right? So first, it is very hard to do simulation when you have objects in different matters. And second, this is even assume you have perfect state estimation. So the second problem is vision is hard, therefore state estimation is hard, right? It is we just spend time talking about how you can get physical properties out of visual observations, but that's definitely not perfect. So state estimation is hard. Even with perfect state estimation, physical simulation is hard. Right, so that's the issue when you want to have a simulator used in some ways, different ways in the system. But it does have the nice property that it allows you to do any type of action condition predictions because it's physics-based. And video generation models are in some sense complementary because first, they're supposed to be very general. You can take any image and you should be able to produce realistic videos. And second, they're supposed to be able to do all of these completions because they have learned, you can call it common sense, or it's more like visual priors about what a realistic image and video will look like. So even with occlusions and missing regions, it should be able to complete these. But they cannot take actions as input yet, right? So you can argue that Genie 3 can take some actions as input, including going forward and backward, and maybe some language as actions. But the type of actions you really need for video generation models to be useful for physical simulation and eventually for robotics, you really have to specify actions in a very specific way, right? For example, in my case, if I'm grasping this microphone, right, I have like 5 contact points with my fingers, and every contact point, the magnitude of the forces, the size, the regions of the contact point, they already matter. And if I, just like change very, very slightly the way that a certain finger interact with the microphone, the object will drop. Right, so you have, actually I have 5. I thought I only have 1. Great, thank you. I have 5 minutes. So the way you interact with these objects requires you to specify actions in a very specific way, which is something that definitely not something the language can describe. And I doubt, anytime soon that video models will be able to do it. Maybe eventually, but it's not going to be a short-term issue because we just don't have data on even these type of actions and how they can be specified. So the idea now becomes very simple, right? We just have a hybrid model. Is it possible for us to first have a visual physical generative simulator? So if we go back to the diagram I showed at the very beginning, I said at first we have intrinsic and intermediate representations. In second, we can have them as decision target. In some sense, I would say in this hybrid paradigm, we're integrating the two because you're having these preaching foundation models and you're distilling them so that you get all these physical object properties. But at the same time, it's not done because you now take, again, these physical object properties and send them back, for example, as conditions of these foundation models, right? So that these foundation models are becoming much more physics-based or grounded because they are taking these physics-based intrinsics and their intermediate representations as the conditions. So you really close the loop by thinking about how physics and foundation models may interact with each other. In the case of Wonder Plate, right, the work I just presented, at a high level, what we did is you have a single image, and you want to let it go through or build this kind of hybrid generative simulator, which has a physical simulator and a video generator. What you did is you first try to reconstruct the scene in 3D. For example, you can use the Wonder World framework I just showed. And of course, the reconstruction is not going to be perfect, right? You're going to have a lot of missing regions. But even with the partial imperfect reconstruction, you can let it go through a physical simulator. And the physical simulator is going to do something, right? Just in the fluid simulation case, now it can do something, it's trying to think about how the fluid is supposed to interact with the shoe. But you can see all these visual artifacts here, right, on the shoes and stuff like that. Okay. So what you can do now is you can send these imperfect but maybe intuitive physical simulation output as conditions to your video diffusion models, right? You can take depth map or optical flow as the conditions so that the video generation model is supposed to generate something guided by your physical simulator. It's supposed to look similar but much more visually realistic. And similarly, you have the problem that it's just a video. It doesn't have an underlying 4D representation. So you can re-optimize the underlying 4D representations through differential simulation rendering to make it look like the video observations. Right, so then you really get the best of both worlds because you have a 4D representation, so you can see it from different viewpoints. It's physics-based, so that it's supposed to look physically plausible, and because it's guided by these video models, it's now much more visually realistic as well. Right. And yeah, and it actually works with different types of objects, like a rigid body interacting with fluid, or think about how the smoke can go up and you can drag the shoe around, and cloths and rigid bodies like boats interacting with each other. as well as because it's action condition predictions, right? You can take the same scene and you can think about how it look like under different types of actions. Yeah. So this is again done by my PhD student Koven and Jiajun, who did earlier this quadruped stuff. Okay. I only have 2 minutes probably. I want to just quickly highlight one additional thing, which I don't have time to talk about, but I'm actually getting more interested in it, and hopefully maybe there's something more to do. But what we have right now is also extremely preliminary. That is, once we have a lot of these raw observations and these foundation models, we want to distill from them. Mostly we have been using image and video diffusion models, but language models also understand a lot of things, right? So to what extent has the vision language models have been able to represent the world and capture things that are maybe at a high level in the sense that it's not just like detailed physics, but it's maybe more about the semantics as well as the structures of the world. So the thing we did, which I will just quickly go through, is called C language. So in this case, we want to put together 3 things. That is, when I say there's a chessboard, I actually mean a lot of things. First, I understand the chessboard need to have different chess pieces and board, and the chess pieces have to be black and white. The board has to be black and white, and pieces have to be black and white, and they have to form the same layout. Right. So in some sense, when I say chessboard, I actually mean a lot. There's so much common sense integrating a single word, and which is something that these language models actually capture pretty well. Right. So, and then we want to represent a scene, realize there may be 3 things that really matters, in some sense, or 3 categories of information. The first is, there's kind of repetitions or the regular structures of the chess pieces and the chessboard. So this is what we call a structure, which is often best represented through some form of programs. And the second is, how can I know? Oh, the chessboard, it has pieces, and the pieces, that includes the rooks and knights and bishops and stuff like that, right? So these are the semantics that are often encoded by the words. And finally, there's the thing that we just spent all the time talking about, which is the underlying intrinsics, the geometries and physical properties and appearance fields and stuff like that, right? Which is often very hard to describe in natural language or in programs, but they're best captured, through kind of latent embeddings that are learned. So in some sense, you feel like these 3 integrations of the 3 really give you the best of everything. It's a minimal, it minimizes description length, it brings interpretability, and it's also very expressive. So we thought, is that possible for us to build a representation based on a hybrid of these 3 things? For example, when I say there's a moai or whatever, these kind of famous attractions on the island from Chile, right? So I understand, right, there are 7 of them. That's because how the scene is supposed to look like. And the 7 statues are all similar, like roses, but they also, so they have the same name, but they also have slightly different intrinsics, just like the roses also look slightly different. Right, so the use of the programs allow us to easily capture loops. The use of words allow us to support very easy editing. So now I can say I want to have 2 moais instead of 3 of 7 and have them face each other. And the use of embeddings allow us to even do visually guided editing, such as I can say I have these now the 2 moais, but I want the textures to be changed or geometries or whatever features to be changed so that the texture look more like this vase. Right, but what's the texture of this vase? I can't even say it myself. But I can take a latent embedding of the vase, of the texture of the vase, and apply it to the texture of the moai. Right, so I can support visual editing and visual prompting as well. So in this work, allows us to different type of texture 3D generation editing, such as I can generate, as I said, a chessboard at game start. I can make a starting chess move. So what does it mean by making a starting chess move? What is really being changed in the scene representation? It's not the embeddings or geometries and texture of the pieces, right? It is basically extrinsics, right? The particular positions of maybe one piece of among all the pieces. So this was again done by my PhD student Yingzhi, who did the very first rose work. And other examples, for example, we have a famous painting, right, the Son of Man. I can type in, say, generate this thing in 3D. I can actually get a 3D version of a painting, and I can edit it. I can say, move the apple to the left, right? So everything else is the same, but then the extrinsics, the pose of the apple has been changed. As well as I can generate an 8-layer, 3-color Jenga game at game start. I can remove 2 blocks from the second top layer, and the tower should not fall, right? So they all specify different distribution of possible editings in different spaces, either in the embeddings or in the programs or in the words. And we've seen this example before. making the statues face each other. And you can do it in 4D as well, right? Because the motion is, again, another program-like structure which you can specify on the extrinsics. I know I'm out of time. I'll just wrap up in 1 minute. So, basically when I say carousel with a small canopy, right, it specifies, okay, the poses of these individual pieces should move in a specific way. So you can also write it as a programmatic representation on the extrinsics of objects, as well as when I say there's a solar system, right, implies there has been a sun and 8 planets now, and the motions of these different planets. Okay, so to summarize, so what we want to do is how can we model this visual 4D world through, on the representation level, on intrinsics, and as well as how they couple with the other things, including the representations have to be learned by AI or foundation models, as well as physical simulations. All right, so there's this fundamental question that we also want to answer. That is, what are the things that we want to model in the learning systems, and how do they help our understanding as well as generation? And how do they interface with physical simulation and these pre-trained models? And our answer has been, we are trying to, and again, there are different ways of using these, but we always try to tie them together to the underlying object intrinsics or physical properties, because first, they're very universal. It applies to every type of observations you've seen before, right? Every image, every videos or even sound or audios, right? They're all based on there's underlying physics, which we always try to understand, and physicists have to try to understand for centuries. And they're causal, which is very important because it allows you to directly specify the actions or type of interventions you want to have, and the system should be able to just causally respond to your actions if your entire modeling is physics-based. By thinking about how the interface with foundation models allows you to use in-the-wild data, which can be either in the form of pre-training in the foundation models or in the case of self-supervision. And it allows us to leverage knowledge from physics, but also potentially synthetic data, which I didn't talk too much here. And that's also a very important source about how we can supplement in some strategic way with the limitations of real-world data. And it gives you different type of, I would say, a certain level of interpretability because it's all physics-based, as well as the physically grounded controllabilities as well. Thank you.
Okay, thank you for the great talk. Any questions? Yeah, you can use the mic. Oh.
Okay. Thank you. Yeah. Yeah. So wonderful talk and very enlightening. I have one question, so we can talk offline later.
We'll probably talk offline, but
so a lot of the work is based upon, for example, differentiable rendering or a simulator, which is differentiable rendering is also one of my colleagues at UCSD, Chinmao Li, is a leading research direct. Yeah. However, like your original idea, very kind of motivating kind of thinking is trying to learn the underlying physics that are kind of more or less top down, if you will, or high level, right? But yet the learning process has been achieved using differential rendering, which essentially say, oh, if I adjust this parameter, then how much it's changing this particular pixel value, then we make these changes. So this kind of learning process versus motivating thing sounds a little bit contradictory to each other. So my personal view is probably these things should be learned in separation as opposed to really fine-tuning particular thing, or not fine-tuning, but level change a particular parameter to change the pixel kind of thing. So I don't know. So what is your thought about this?
Well, I think, Joanne, that's a good point, right? So let's say there's idea one, there's idea two, and there's some hybrid of those. Right? One of the biggest motivation behind our switch from idea one to idea two is in idea one, you have a simulator in a loop, and the simulator itself is very constraining. Right, it is becoming essentially what you said. You change some physical parameters and see how simulator is going to respond to it. In the second version of idea, right? So if you're just trying to distill everything from a video diffusion model, there's very little physics, right? The only physics here is what do I care, right? So if I have an image video diffusion model, I can directly generate videos. But if I do care, some level of geometry and texture, I can use it as an output. They only use to physics is only used to specify the target, the output, and there's no physical simulation there at all, right? So I was all I need is just like, oh, I care about geometry, and that's where physics is. So, and finally, when I say there's a coupling of the two, I think it was like, you want to think about physical simulators in a more broader sense, in the sense that I think in practice, in the specific work we have done and the results have shown, they still more or less rely on some type of differential simulation. So it has the problem that you said. But the goal has always been, think about if you can close the loop, then you're using a physical simulator in a different way. That is, you just don't just take it off the shelf, but think about how the knowledge you have distilled from these video diffusion models or any kind of learning-based data-driven models can help you to guide and fix problems. Because I used to use the word augmenting physical models, but I feel like that is not even enough because sometimes it's like the fundamental ways of his physical models operate can also be changed. So it's not even just augmenting, it's maybe more like revolutionizing. But so I think there's a hope that is we can distill physical properties and use it to suggest how physics should work, and by even replacing or revising a lot of these physical simulators. And that's something that we've been thinking about as well. But it is true that except for the work that we're doing purely distillation, even with these hybrid works, eventually, at this moment, we have to go back to some sort of differential simulation, which then is constrained by what these differential simulation can support. Does that make sense?
Yes, yes. Yeah, great. Yeah. Okay. Thank you.